Good morning, good afternoon. Welcome to Biomass Canada Cluster Project Updates webinar series. My name is Mahmoud Abadian. I'm a research associate at the University of British Columbia. I work with two research groups at UBC, including Biomass and Bioenergy Research Group, as well as Forest Product Biotechnology and Bioenergy Research Group. And I work on biomass logistics and supply chain. Today, we have the fourth webinar from this series. We had three webinars in April and two of them in May. And this is the fourth one. We are going to again provide updates on two activities, activity number 12 and also 13. And it's mainly focusing on biomass production, logistics, and supply chain. And one of the focus is actually on pelletization of agriculture biomass. We are going to give some update on supply chain, production, and also storage and handling of agriculture pellet. Just briefly give you, if you haven't heard about the Biomass Canada Cluster, it was established in 2018, led by BiofuelNet Canada Network and with the financial support from Agriculture and Agri-Food Canada's Agri-Science Program and also contribution from industrial partners. The focus is to enhance the contribution of Canadian agriculture biomass, the growing Canadian bioeconomy, and currently we have 10 activities or projects. We look at different aspects of agriculture biomass from production to logistics and supply chain, also bioconversion past phase, and also market development. And today's focus, as I mentioned, that is mainly on production and logistics and supply chain for agri pellets. So the two PI for these two projects are Dr. Shab Sukhansand, who is an adjunct professor at the Department of Chemical and Biological Engineering, and also at the University of British Columbia, and the research leader at the Biomass and Bioenergy Research Group, and is leading activity 12 and jointly with Dr. Donald Smith, he's joining activity 13. Dr. Donald Smith is a distinguished James Mackey professor at the University of McGill. And as I mentioned that we are working closely with Don on activity 13. In addition to Shab and Don, we also have other colleagues from Biomass and Bioenergy Research Group. And when I give them actually, I let them introduce themselves when they have, they are supposed to present their slides. So before I give it to Shab to start the activity 12, just keep you, just to remind you that this webinar is being recorded and a copy of recording and slide will be posted on Biomass Canada Cluster website. And also, if you have any question, please make sure that you put it on a Q&A box, not chat box. So that's going to make the job easier for me to ask this question from the panelists. So with that, Shab, I hand it over to you, and he's going to give you an update on activity number 12. Thank you, Shab.
Thank you, Mahmoud. Good morning, good afternoon, good evening, wherever you are. We're delighted to make presentation today on of activities which happen to be two activities within Biomass Cluster. Both activities are focused on agricultural pelletization, specifically on post-harvest technology. The first one would be the ag pelletization activity number 12. So if you go to the next, this is an acknowledgement that will make that this funding comes from Canadian Agri Partnership through BiofuelNet and Biomass Cluster, which is BiofuelNet is a holder of industrial partner for this project, for this activity is Wood Pellet Association of Canada and a smaller company, GS Bioresource Systems. Just provide a background on this work that we do. We start really from the state of wood pellet industry in BC. It is an established business that is going forward. On the left-hand side on this chart, you see that we're producing in BC at about 2.5 million tons of pellets. In fact, the whole Canada is about 3.5 million, and that brings around $400 million 2020 type. So this business, which was established about early 2020, 2000, is progressing, but at a fairly slow rate when compared to the growth of the industry worldwide. There are two issues that is really facing production of pellets. One is, of course, the kind of the issues that comes out regarding the sustainability of wood for production of pellets and burning pellets for production of power and heat in other countries. So there is a adverse publicity on these issues. So this is kind of put a little brake on the growth of the pellet industry in Canada and elsewhere. There is also an issue of reduction in timber harvest. As you know, the pellets are produced from residues from forest, and there is a reduction in timber harvest, and because of that, there is less residue material available to make pellets, and it's becoming more expensive actually to access that material. If you go to the next slide, Mahmoud. This slide shows the current distribution of pellet plants in Canada. As you note, most of the pellet plants are in BC because that's where the most wood is available. Also, there is a concentration of wood pellet plants in Ontario, in Quebec, and there are a few, like 4 here, as you see, in Alberta, and a couple in Manitoba, and none in Saskatchewan. There's a couple of plants also, very small production in New Brunswick and Newfoundland as well. So I'm sorry, New Brunswick, at least there is 5 plants operating, but Manitoba and Newfoundland is that they have a couple plants in there. So as you see, the pellet plants are located mostly in the West Coast area, where they are shipped using ocean-going vessels in there, and pellets are produced in this area mostly are either exported in the US or from New Brunswick now are exported as well to UK. Quite a number of pellets from BC goes to Japan because of the access to shortest route here as well. Go to the next one. So as noted in the previous slides, most of the pellets are located into the 2 ends of the country, as you noted, and where the forests are. But there's none in the central area of Canada, well, western mountain area and central area, as you noted here, in British Columbia, in Alberta, Saskatchewan, and Manitoba, where most of the agricultural material is grown. As you noted here, the blue color shows the million hectare of the land that, for agriculture that are located in these areas, as you see how they are distributed, and the number of the farmers, of course, farms are also located in this area. So there's a tremendous amount of agricultural material that are being produced. As you see here, there are like about 30 million tons of residue. This is net residue available after deduction for soil conservation as well as for animal use. So there is a tremendous potential to produce ag pellets in this area, in these areas that there is no any wood pellet plants or wood pellet operations in there, and hopefully to be able to produce ag pellets to augment the existing wood pellet industry. Go to next. So along with that, there is a number of challenges that we have to overcome to make ag pellets a sustained industry in Canada. Ag pellets have a higher ash and chlorine content than wood pellets. So it's tough to meet some of the international standards in terms of the maximum ash content and chlorine content that's specified for pellets. Ag pellets, they have a low lignin, so the natural binding in ag pellets is lower than what we have in softwood, so we have to use binders in terms of producing durable pellets. The yield of ag residue, like ton per hectare, is lower than wood residue, so this means the concentration of the ag material on land is much less, so it's costly to collect the material from the land because of the kind of thinly distributed material. The bulk density of baled biomass is much less than the density of chipped wood. I say much less, probably about half of that in terms of the density. So the material has to be densified in order to be able to ship or store and ship it economically. Agricultural farms are distributed around the country, but mostly in Saskatchewan, Alberta, Ontario, and Quebec. Because of this, the distances between agricultural regions to export ports are long. And then there's a number of other issues that we have. For example, one of the major issues is acceptability of the ag pelletization by farmers as well as by investors. So these are the number of challenges, and we started our project basically 2 years ago, 3 years ago, to kind of address these issues one by one. And following this presentation, we'll sort of show that how we go about addressing these things through my colleagues here, that they will make presentations. So the two goal statements here are evaluate the production use of agricultural pellets as a feedstock for low carbon bioenergy and other bio-based products, production of durable agri pellets with consistent quality at affordable price. So these are the two main goals that we set for ourselves in this activity and trying to achieve these goals. We go next. So the project is divided into three, or this activity divided in three sections. One is a discussion on logistics. The next section is quality of the material, addressing that. And the final one on storage. Mahmoud will do the logistics, Hamid will do the quality, and Fahime will do the storage. I think, Mahmoud, the next is you, right?
Yes.
Yeah, go ahead. Yeah, please.
Thank you, Shah. Okay, so as Shah mentioned that one of the tasks for this activity looking into logistic and supply chain for agri pellets. And I want to just emphasize that we are trying to piggyback on the existing supply chain we have for grain and wood pellet, like using the same like port terminal, a storage facility. We use the same rail cars if you want to transport a long distance. So that's actually the focus for this task. So one of the, if you want to establish a supply chain, we need a market. So that's why in this activity, we have looked at two potential markets for agri pellet. One of them is basically, as Shahab mentioned, that how we can support the Canadian wood pellet industry to meet the global demand, because the demand for wood pellet is growing. So that's why we have looked at the globe, how we can actually export agri pellets to support the wood pellet industry. And another potential market is just, as you know, farmers use a lot of energy for grain drying. They use energy for buildings. So what is the opportunity of actually using agri pellet as a feedstock for, mainly for heat generation in farm communities? So that's the domestic market. Quickly mention this. This is a publication we had last year. I'm not going to discuss this one that was presented last year, but if you want to, if you're interested in this topic, you can find a manuscript online. So it's basically, we work with Biomass team. It's based in Saskatchewan, the Agriculture Agri-Food Canada, Biomass Inventory Mapping and Analysis Tool. And we found 6 potential locations that they have high yield. And we assume that we produce ag pellet in this location and then export it to the ship it to the Port of Vancouver. Then from Port of Vancouver, we ship it to the Western Europe. Then based on that, we estimated the cost, we estimated the price, and we did a comparison between wood pellet and agri pellet. So again, I'm not going to talk about this one. That's not the focus for today. But again, if you're interested, you can take a look at this manuscript. And if you have any question, we would be happy to answer those questions sometimes after the webinar. Today, I want to mainly focus on domestic market. How come, what is the opportunity of using agri pellet for, mainly for grain drying? Because it's a very energy intensive process. It's almost 15 to 20% of the total grain production. And also the farmers, they need a lot of energy in a short period of time. And that's not, if even they put the cost aside, they have to deal with the greenhouse gas emission, because with the carbon pricing from the federal government, they have to pay more for use of energy. So we have been working with a farmer in Whitbury in Alberta, and the farmer is currently using propane. So that's a source of energy, and they have a conventional cross-flow dryer, and they dry mainly wheat for in their farms. And so the question is that what if we, instead of propane, we use biomass, like either wood chips or wood pellet? I just want to emphasize that for now, we did a comparison between propane versus wood chips and wood pellet because we have data. We have, at least for wood chips, wood pellet, we know the supply chain, we know the cost. And then in the next step, we are going to do a comparison with agri pellet because we are still generating data from our lab result. So that's going to be the next step. So that's why for now, it's going to be mainly wood chips and wood pellet for grain drying. And that's going to, I'm going to provide you with some of the results. So we have looked at different scenarios. We have seen an increase in the price of fossil fuels recently. So how that's going to impact the growing cost for farmers. And also, we projected the price of fossil fuels and biomass in the future. So these are 2 scenarios. And two other scenarios are policy-based. Scenario 1 of them is federal carbon pricing, how that's going to impact the growing costs. And also, recently, the Agriculture Agri-Food Program, they announced a new program. It's called Clean Technology Program, and that's going to provide some capital cost for farmers. So how this type of incentive is going to impact the growing cost. So we have looked at those other scenarios. Just want to give you a sense of the changes in the price of propane. So this is from since 2017. So you see that not only fluctuation is going to impact the farm decision and also the revenue, but also recently we have seen an increase in the price of fossil fuels, including propane. And you know the reason is mainly the war in Russia, like between Russia and Ukraine. It has actually created a crisis in the energy market, so that has impacted the price of propane recently, and also the carbon pricing from federal government. As you know that currently we are at $50 per ton of CO2, but it's expected to increase actually to $170 per ton of CO2 by 2030. And that's the impact on the propane price. So you see that for every $20 per ton of CO2, it's about 3 cents per liter for propane. And so we quantified how this carbon pricing is going to impact the drying cost. So just some results I want to show you. So this is the drying cost, $1 per megawatt hour. So using propane, wood chips, and wood pellet. And you see that most of the cost is actually for propane is mainly the fuel or the feedstock, not really the capital cost, because it's a very, you know, that propane dryer are very well established technology. The cost is very low compared to wood pellet and wood chips. So you see that a majority, almost 95% of the cost is related to propane. And so every time the price of propane increases, that's going to directly impact the drying cost. But wood chips and wood pellet, at least wood chips is almost like, you see that the capital cost is quite significant. Wood pellet is a bit less sensitive to the capital cost, is mainly the cost of the wood pellet. But the main message here is that doesn't matter how much grain you want to actually dry. We look at different scenarios, how much grain we dry. Wood chips and wood pellet are more economic option for farmers rather than using propane based on the current price of propane. So I guess that's the main message here, especially that again, most of the cost is coming from the fuel, not really from the capital cost. So that's the main message here. And also, if you want to do a comparison, how much cost saving farmers can actually expect, the blue one is wood chips. So you see that as you increase as you use the burner for drying more grains, the capital cost actually reduces because you're utilizing your dryer more. So you see that the cost saving could be from like almost 32% to 60% if you use wood chips, and for wood pellet is about 50% cost reduction compared to the propane. So it shows that for farmers that actually use dryer for longer period of time, using even wood pellet, wood chips, or agriculture pellet makes more sense because that's going to increase the utilization rate. But how the carbon pricing is going to impact. So again, the green and yellow one is for wood pellet and wood chips. You know that the carbon pricing is not going to impact the use of biomass. Biomass is not affected by the carbon pricing because it's a renewable source of energy. But you see that the red one, you see this red one, this is the additional cost for farmers if they keep using propane. So as the carbon pricing increases from, let's say, 0 in 2019 to $170 in 2030, you see that the amount of increase in the cost could be quite significant. So that could be even motivation for farmers to take a look at biomass, either forest biomass or agricultural biomass, to replace propane. So I guess that, again, that's what we are trying to quantify that amount for farmers, so that farmers can actually make a better decision if they want to switch from biomass to from propane to biomass. So again, the main message, my last slide is that again, under all scenario, biomass burners are more economic options compared to the propane ones. And also the cost saving for farmers could be very significant if they switch from propane to wood chips or wood pellet. It could be from 35 to 58%, depends on the utilization rate. And the last point is that every $10 per ton of CO2 increase in the carbon pricing adds about 2% of total drying cost. So as the carbon pricing is going to increase, that again, the amount of additional cost for farmers could be significant. So that could be, again, a motivation for farmers to look into biomass more seriously to displace fossil fuels. So with that, I finished my presentation. I guess the next presenter is Hamid. Hamid, please go ahead.
Hey, hello everyone. Thank you so much, being with us today. Thank you, Dr. Shahab and Mahmoud, for your introduction and presentation. My name is Hamid. I work on task 1 of activity 12, which is about material quality and collecting agri-pellet production data. Today, I present a little bit of our progress about the what we have done on the agricultural samples we tested, and some of the next steps that we plan to do during next year. Next slide, please, Mahmoud. Okay, so as Dr. Shahab mentioned, agricultural material has, it has some unique properties, characteristics that there are barriers against using them as a commercial bioenergy feedstock. One of the most problematic one is the huge variability in properties, physical and chemical properties. These properties change seasonally, geographically, and also the way that they have been grown. They're very difficult to grind and reduce the size of the material for further bioenergy application, pelletization, and conversion. And the mineral content and ash content is very high compared to woody biomass, usually more than 10 times of ash content compared to woody material. The lack of lignin is a big problem compared to woody material, so it makes it a little bit harder than woody material for pelletization applications. And another problem is that most of the experience in handling of agricultural biomass are very in farm-based scale, and there's very little industrial experience in handling this material for bioindustry. So our research in activity 12 for material quality testing task 1 was mostly oriented for solving these challenges. So Mahmoud, would you please go next slide? So in the first step, we collected some 4 species of wheat straw, corn stover, switchgrass, and flax straw from different. What we tried to do was to understand the grindability of these materials using hammer mill at different moisture content. And the key message of our measurements in this part was that it was very difficult to grind the material down to 2 to 4 millimeter of particle size for pelletization application. The reason is that the nature of the material, the fiber length, and the properties of the material are in a form that the grinder rejects a big portion of the material during grinding in one round. So the material needs to stay in the grinder for a longer time. And we observed that the amount of energy consumption for grinding agricultural material is more than woody biomass. And this the grinding power consumption also depends on the moisture content of the material. When we increase the moisture slowly after 10-12% of moisture, and the amount of energy that material needed to be ground down to a couple of millimeter increased significantly. Although all of the materials that we received were in the range of 10%, 9 to 11, 12% moisture, but because they're all most of the time are stored in open area, we should be careful because they can be exposed to hard rain and these moisture content increase. Next slide, please. The next step of our research was about measuring mineral profile of the material and the ash content. Minerals are, they form salt that are very corrosive, and they end up in form of ash after combustion process. So we purchased an XRF unit. We did a lot of about 100 XRF measurements and developed a procedure of quantifying the mineral measurement and chlorine measurement. We tested using high chlorine content woody material to test and validate this procedure. And after that, we applied a method of a quick 5-minute washing and pressing the material to understand how much we can reduce the concentration of the minerals from the biomass. On the woody biomass, the results were very promising, especially for the chlorine concentration, but we applied the same procedure for agricultural material that I will show you in the next slides. Our measurements showed that all of the agricultural samples that we tested, they needed a demineralization process to reduce the mineral and ash content. Wheat straw specifically, it has substantially higher value of chlorine, silicon, and potassium than all other samples that we tested. Although all of them were far above the ISO standard levels. Because of the higher chlorine and silicon content, wheat straw also had a much higher ash content than other samples, something in the range of 7%. Although we compared the wheat straw that we tested with some other values in the literature, there were some range of between 5%, even up to 15% of ash content based on how they harvested the material. So next slide, ma'am. So we applied the same procedure of cold water washing, a 5-minute washing and then a mechanical pressing on the agricultural material, and we tested we tested on the woody biomass. The results were very promising, but for very selective elements. We found that about 80% of the chlorine that was in the material we could wash it off, and about 50% of the potassium. It was very fortunate because the chlorine is a very problematic element in combustion process. It's a very corrosive. But the data in this table shows the results for wheat straw and flax, but the trend of the the results were the same for all other agricultural biomass. So chlorine and potassium, we could remove them substantially, but for other elements, for example, silicon and calcium, the reduction was not very significant, mostly up to 10%. After that, we started our pelletization measurements using our smallest scale pelletizer machine, a single pellet machine, MTI. We did this test to understand the compressibility behavior of the material. So this machine, the good point of this machine is that it's very controlled condition. We can adjust all parameters, temperature, compression, and everything. The observation was that in a single pelletizer and very controlled condition, the pellets were visually very durable and in a good shape. And also there was a big difference between among these tested materials, that some of them were very sticky and they needed much higher energy to form pellet. These data all will be directly will affect the amount of energy consumption, and in another word, the production capacity of the pellet mill. So the data and the result that we got from this single pellet testing, we can use them in our logistic model to calculate the total amount of energy that we have to consume for making pellets. So next slide, Mahmoud. So after that, we made some quality measurement on the pellets. The interesting result were that the density of all of the pellets that we made, they met the ISO standard. They were all above 1.25, which was very good. The hypothesis, the reason must be because of the form and shape of the particles, the agricultural materials. After grinding, the thickness they're very thin compared to woody biomass, and they can fit all the gaps on porosity inside the pellets. And it must be the reason that the density of the pellet are very high. The durability was also, most of them were more than 90%, but they haven't met the standard. The ISO standard says more than 97.5% for grade A pellets and more than 96% for grade B. But our measurements were mostly more than 90%, but they haven't met the standard measurement. We can say that there were two reasons for that. Usually the lab pelletization trials, they make pellets that are a little bit less durable than industrial pellets. And also the way that we measure the durability of single pellets, they give slightly smaller numbers than the tumbler system, which the standard looks for. So next slide, Mahmoud. So in search of biomass treatment technique to meet the durability specification, we tested the effect of biomass hydrotreatment on the durability of the pellets. We did 4 rounds of biomass treatment, and then we made multiple single pellets and measured their durability. In the first, so we did 4 sets. The first set, the dry biomass was exposed to continuous steam. The second set, biomass with low moisture content up to 15% were exposed to dry heat. In the third set, high moisture content biomass was exposed to heat, and in the fourth one, the dry biomass was exposed to water. The results show that the optimum treatment temperature and the duration depends very much on the method of the treatment. For example, if we treat moist biomass. The optimum temperature is about 140 degrees C, and the duration should be about 15 minutes to achieve the most durable pellets out of the material. Or in another technique, if we expose dry biomass to hot water, we need to heat the material up to 180 for about 60 minutes to achieve the most durable pellets. But the key point is that using this hydrotreatment, we could change the properties of the material, mechanical properties of the material, in order to reach a pellet durability of about 98%, even in the lab scale pelletization. So it was a big improvement, because it's very hard to increase the durability from 90% to 98%. And it was a big improvement for material property. So, and then we switched from our batch single pelletizer to a continuous system, a 5 kilogram per hour pellet machine, CPM. We studied the effect of particle size, moisture content, material flowability. Our observation was that the first and the most important criteria for making pellet in a continuous system was the flow rate and uniformity of material flow into the pelletizer. This was not a serious issue in pelletization of woody biomass. Again, this property, this issue can be correlated with the shape and the structure of the agricultural material after grinding. They are very long and very needle shape, and the flowability is much harder than woody biomass after grinding. So we found that the agricultural material should be ground more than woody biomass in order to have a smooth flow of material in the feeder of the pellet mill. So in our grinder, the largest screen size that we could use to reach to that condition was a 1/8, about 3 millimeter screen size, which gives particles in range of 1 millimeter, 1.5 millimeter range. So this one was one of the difference with the pelletization of woody biomass, but the moisture was really in the same range. We could reach to pellets for both woody and agricultural biomass in the range of 10% to 12%. In our continuous CPM machine. But our hypothesis is that steam conditioning and adding binder will give a big improvement in the quality of the pellet. Our next step in pelletization experiments is to test steam conditioning, the duration exposed to steam, and the temperature of the steam, and also adding binder to see how the pellet quality and pelletization process will change. So this, I'm pretty sure Mahmoud is going to talk a little bit more in more detail in activity 13 about our pilot scale pelletization. But the pilot scale machine that we received, we moved it to Four Peaks Farm in Alberta. The unit has all of the components of an industrial pelletization process: mixer, grinder, steam conditioner, pellet press, and also a cooler. And the advantage of this unit is that it's a mobile unit. And now the unit is in Alberta. It has been CSA approved, certified. And the next step is to run the machine and mix some pellets. So I know that Mahmoud is going to talk more about that, because he has been in more closer conversation with our partner. So the lessons we learned from our testing in the last year was that first, size reduction is difficult. The moisture content is very important for grinding the ag material. It preferably should not be more than 10 to 12%. Washing and pressing can reduce the mineral, can change the mineral profile and reduce the chlorine content, wash off the 80% of the initial chlorine and 50% of the potassium, but not very efficient in removal of calcium and silicon, or maybe some other elements. We need to extend our research for demineralization process to push the material quality closer to the standards. And also our hypothesis is that the steam conditioning and binder will change the pellet quality significantly and make it a much better commodity for the market. So our next step is to test the effect of these two conditions in continuous pellet mill in the lab conditions. So thank you so much. I think Fahim is going to present the next slides.
Thank you, Hamid. Thanks everyone for joining us. My name is Fahime, and I work at UBC and Wood Pellet Association of Canada and then it's a pleasure to present our work. So Shahab, Hamid, and Mahmoud talked about ag pellets or ag residue logistics and pelletization, pre-treatment, drying. And I would like to talk about another component in our work, which is focused on safe handling and storage of ag residue and ag biomass. Next slide, please. So in the storage of agricultural biomass, the major problems that could arise during handling and storage are mostly connected to dust formation, off-gassing, and self-heating, and of course, biological hazards. For biomass, any type of biomass, and in particular agricultural biomass, because the seasons are very short, storage is very critical. So we've learned from our knowledge, from our experience from wood pellet industry, that self-heating and off-gassing could lead to really serious accidental fires as well as danger to workers. So we can really use our knowledge from wood pellet industry that has been in fact very successful to help us make a very safe industry, to really evaluate the potential of self-heating and off-gassing, and as a result, oxygen depletion in storages of agricultural material, and help us to develop standards that use for storage of agricultural biomass. We've been really looking into determining the parameters that could contribute to self-heating during storage of agricultural material, and really understand the contribution of each of these parameters, what the heat that is produced due to any of these processes, such as auto-oxidation, moisture addition, temperature of the storage, and humidity changes within the storage. This particular part of the work that I will be presenting is done purely experimentally. However, there is a work being done on modeling of self-heating that is led by Dr. Hamid Rezai. We've been also looking into developing methods that we can measure agricultural pellet properties and look at their compliance with ISO standards. And in particular, I'm referring to the standards that are focused on off-gassing and self-heating of agricultural pellets. Next slide, please. So on the top, the diagram, you can see the sequence of operation for handling baled herbaceous biomass from farm all the way to the storage. So when they get to the storage, they are converted to pellets. The dry straw and hay are very much prone to disintegration at every stage within this operation. However, most of the physical damage and loss of material actually happens during grinding and any size reduction unit operation that you have within the process. And the chemical and biological deteriorations usually occur during biomass storage if you're not really protecting the biomass from any of these elements. The diagram below is really showing the processes that are involved in deterioration of herbaceous biomass during storage. As I mentioned earlier, there are different processes that are involved in deterioration of herbaceous biomass during storage. So of course, microbial activity initiates the growth of mold and breakdown of these carbohydrates. And then further deterioration happens when you have heat generated and moisture migrated within the bulk of material. And then of course, the spoiled and deteriorated biomass will then have lower calorific value and lower properties. And of course, it could lead to issues for workers that are handling this type of biomass. When you cut fresh biomass during grinding, a number of biological and physical and chemical processes take place. And when you have smaller particles, the greater the rate of biological activity would be, because you have now increased surface to volume ratio. And in a pile of biomass, excuse me, due to the limited air passage or airflow that you have within the bulk of agricultural biomass, and in fact, very low conductivity of herbaceous biomass, then the heat accumulates within the pile of agricultural biomass, and then it could reach up to 60 degrees. And then the wider the pile is, the harder it would be for the heat to dissipate from the center of the pile to outside, and the greater the potential of self-heating and heat rise will be. When it gets to about 80 degrees or so, all of these biological activities will cease, and other type of reactions such as oxidation, charring, hydrolysis, and water transport and absorption would take over and are dominant. Next slide, please. Here, I would like to quickly show you two graphs that are really representing the relationship between relative humidity. On the left side, you can see the relationship between the relative humidity of the air and moisture content of biomass. So this work is done by some of my colleagues in our group, and we have tested a lot of different types of biomass. So for example, when you look at, for example, when the relative humidity of the air is at about 80%, and the moisture content is expected to be around 15% on wet basis. And for 80% humidity, temperature of 20-30 degrees, this could be an ideal situation for microbial activity to happen and mold growth and so on. On the right side, you can see this relationship, the relationship of moisture content and temperature for different types of biomass, and the large influence that it has on how long you can safely store this type of biomass. For example, when you look at biomass with 35% moisture content, you can pretty much store it for as long as 7 days safely, however, at around 30 degrees. However, if you make it drier, then you can, of course, keep that material safer longer. You can even store it up to 20 days. And of course, we are assuming that the storage condition is not changing during storage. However, if you have some rain or the situation changes, any type of rain or drop of water, then the situation will change and you're not able to keep it as safe that long. Next slide, please. And very quickly, I would like to talk about some of the results that we've got from testing reactivity of materials. So in the previous slides, I did mention how much the heat of oxidation and heat of humidity and heat due to absorption of water are important. So we kind of dived into this a little bit more and evaluated the potential of self-heating for agricultural residue and agricultural material using the isocalorimetry technique, and we recorded the heat that is coming off material during any of these processes. So we used, apologies. We used TAM3, which is an equipment and isocalorimetry unit, and we measured the heat over time. We measured this heat flow over time, and because when you store the material, it could be hours, it could be days, it could be weeks. We looked at the storage time for a long time, and the beauty of this method is that it's not destructive, and we can directly and continuously measure the heat coming off the material due to any of these processes that we mentioned. In 2020, 2021, we developed this method, and over the past 12 months, we have been fine-tuning and optimizing this method. And in fact, we have tested quite a few number of agricultural material and agricultural pellets. And we evaluated the effect of different parameters. Next slide, please. So quickly showing the figure on the left side is showing really the heat release from 3 different types of agricultural pellets that we made: corn stalk, switchgrass, and wheat straw. And then we compared them with the wood pellets for reactivity at 40 degrees. And this is only the heat of oxidation that I am referring to. So the results showed that so far, by far, the agricultural pellets reactivity due to oxidation, the heat of oxidation at 40 degrees is far less than wood pellets at 40 degrees. However, I should mention that all of these pellets are produced using single pelletizer pellet machine, and the demonstration pellet machine that Hamid talked about earlier haven't been up and running yet. But once we do have those more or less close to commercial pellets, we will be repeating these tests using those pellets as well. And next slide, please. So these two graphs are also showing the heat generated due to another two processes, which is one, when we expose the pellets, the agricultural pellets, to humidity, and on the right side when we exposed it to water. The figure on the left side really demonstrates the effect of humidity on heat development for switchgrass pellets when we expose them from 50 to 85% humidity at two different temperatures. A very important thing and a very key result here is that during storage, when we measured the heat at 20 degrees and 40 degrees, we realized that the heat coming off the material at 40 degrees is almost 5 times the heat coming off at 20 degrees. So temperature, storage of temperature in this reactivity would be key to take into account. And on the right side, we kind of exposed the material to drops of water, and we wanted to compare this heat coming off material and then compare it with the heat during when they are exposed to humidity. So you can see the differences in the shape of the graphs. Although it's less than heat caused by humidity, but still it's about 40 joule per gram, much more than heat of oxidation. So these two type of reactivity are very, very significant that we should take into account during storage. Next slide, please. And just quickly going through some of just recapping the results, the results that we've gotten so far are consistently showing that agricultural pellets reactivity, the heat of oxidation is far less than wood pellets, at least with the pellets that we have tested so far for 3 different types of agricultural residues. And from the parameters we have tested so far, again, we have seen that wetting and humidity have the greatest impact on agricultural pellets reactivity. Dry matter loss and deterioration of fuel qualities such as calorific value and heat accumulation, it could lead to spontaneous ignition. And I would like to also mention about some stuff about our understanding on the bales and moist ground biomass. They tend to have really high concentration of bacterial particles and fungal spores that could create a really undesirable storage condition, and again lead to issues in terms of health and self-heating. And biomass bales should be placed on very, very dry and level ground close to the transport road, and we need to make sure the storage environment is dry and the temperature is as low as possible to avoid any issues in terms of self-heating, off-gassing, and human health. And next slide, please. Yeah, I turn it over to Shahab at this point for the few remaining slides, and then we'll take the questions. Thank you very much.
Yeah. Thanks. These are a couple of slides that Biomass Cluster would like us to show that how the project that we're doing is relevant to the terms of Agriculture Agri-Food Canada Partnership Agri-Science Program. So the first one is understanding of technical and economic aspects of agri-pellet production, and use of applications such as grain drying is critical to help farmers accelerate the transition from fossil fuels to locally produced biomass resources. The model that we are developing and we have developed in this project allows farmers to compare and contrast the fossil fuels they are using for operations such as, again, grain drying and the use of biomass. Ash and mineral reduction improves the combustion properties of biomass. Hydrothermal pretreatment of biomass makes the pellet more durable. So that's kind of the relevant part of the work. It is critical success factors are to identify the processes that need to be improved in the production of agri-pellets to make them comparable with commercial wood pellets from a quality standpoint, understand the economics of agri-pellet production and use in comparison with other available feedstocks such as wood pellets, understand the storage and handling behavior of agri pellets in the commercial settings in order to feed them into the existing grain and wood pellet supply chains. Next slide. So work to be completed by March 2023 still is produce ag pellets in pilot scale on the farm and understand, compare the pellet product quality with the lab scale pelletization. Sorry, it's not pelletization, it's pelletization in collaboration with activity 13. Compare and contrast the properties of agri pellets versus wood chips and wood pellets for grain drying, and also really a handling of grain as well. That's where we do the comparison. Conduct techno-economic analysis of washing and hydrothermal treatments. We've done technical analysis. Now we have to do a techno-economic analysis, and which one is more really makes sense in terms of the cost benefit ratio. Evaluate effect of other contributors to self-feeding, including ag pellet porosity and pore size and volume. Next. Okay, thank you. And now we go to activity 13, Mahmoud, right?
Yeah.
We'll leave the questions to the end, right?
Yeah, I guess, yeah, we are over time for activity 12. So we can start with activity 13 and then address all of the questions at the end of the webinar. So as I mentioned, as Shab mentioned, and I mentioned in the beginning of the webinar, we have been working with Dr. Don Smith's research lab at McGill University on activity 13. So he's going, and we have 3 components. So Don is going to present the component number 1, and then Hamid Mohammed and I will present the update on component 2 and 3. So Don, over to you.
Sorry, as usual, I'm muted, but okay. So I will share screen here. Okay, what are you, okay. Sorry, I think I'm working across 2 screens here. I think I need to fix that, so. Okay. All right, can you see my slides now?
Yes, can you make it fully screen, Don?
Sorry?
Can you make it?
Yes,
Yeah.
yes.
Sounds good.
Okay.
Thank you.
All right. Okay, so I'm going to talk about activity 13. And hang on, I'm going to put on my timer here so that I don't go over time. I was asked to keep it under 10 minutes, and I'm going to do that. All right. Okay, so activity 13, I'm going to talk about activity 13. This is integration and optimization of crop residue production. That's my part. Post-processing and handling, and that part is through Shahab Sokasaj and his group at UBC. So we're working together on this, and we're learning from each other. It's been interesting. So this is integration of Biomass Canada work. This is what this activity is in part an effort to do that. So the objectives, there's four specific objectives. So this is to evaluate, develop biostimulants to increase biomass yields and determine effects on key elements, aspects, whatever, of quality of the biomass, to determine the effects more specifically of the biostimulant application on biomass quality with regard to densification capacity. So I'm growing these things and applying the biostimulants, et cetera, and the folks at UBC are very kindly looking at densification capacity. So the other 2 are for the folks at UBC completely. So this is determine applicability, including cost benefit analysis of assisted intelligence tools to biomass compaction operation, and then to demonstrate practical densification at a reasonable rate of wheat straw under production conditions. And this is actually production conditions in collaboration with the producer community. And then overall, this activity is an effort to go all the way from biomass production to the end of the supply chain, where things are ready to be turned over to somebody who would make biofuel or extract high value bioproducts or something like that out of it. So integration of work across the researcher activities in Biomass Canada. So component 1 is what I'm going to present. So this is, evaluate, develop biostimulants, increase biomass yields, determine effect of quality, We've done quite a bit of work on this. So we, over time, well, this is the earliest technology we developed out of this. This is the lipocyto-oligosaccharide, or LCO promoter technology that we discovered the interesting properties of the LCOs, which we were initially investigating in terms of signaling for recognition in the establishment of the legume nitrogen fixing symbiosis. So between the rhizobia bacteria and the legume plant themselves, it turned out they had a whole other set of what I suspect are evolutionarily older activities that have proven to be very interesting. And that technology is now with Bayer, and explain how that happened in the next slide. So a little general background on this. There's a growing interest in biostimulants as a sustainable way to promote plant growth. They don't require very much of it. The concentrations are quite low. And again, I'll show you that in a slide or two along here. But this makes it a low input, environmentally friendly management practice. So as I said already, we've worked with and developed a range of these. We actually started a spin-off company called Biomass Agriculture over 20 years ago now. And BIOS was subsequently, it was subjected to the food chain, sort of the corporate food chain. So BIOS was taken up by a larger Canadian company that moved the technologies along closer to market. They sold themselves for, I think it was 32 million euros to EMD, which was the largest inoculant company in the US at the time. EMD sold a piece of themselves to Novozymes, which included our technology. Novozymes hardwired themselves to Monsanto, and Monsanto was swallowed by Bayer. So it goes. Bayer has been selling that technology quite extensively. I think, again, I'm never sure how accurate these things are, but I've been told it's been going on something on the order of 100 million hectares of agricultural land a year globally, and that Bayer has made something like $1 billion off it. But again, I'm not sure how accurate those things are. Okay, so as I said, we worked on a range of these. They're often microbe to plant signal compounds that we've isolated and identified. The LCO is one of those. It had already been isolated, but we identified its activity in terms of plant growth stimulation. In many cases, they help plants deal with stresses. And this is what the LCOs do, and a number of other ones we've isolated. Often they're abiotic stresses, and often they're the kinds of abiotic stresses that could be associated with climate change. And this is the thing. In some cases, stress responses can involve changes in plant tissue composition, for instance, increased lignification. And if there's an increase in lignification, it's probably good to know that. So biomass with more lignin in it could be better used for soil sequestration. If you want to increase the amount of carbon you're depositing in soil, that increases the soil quality because you have better soil organic matter as a result. And if it has more lignin, the material will take longer to break down, and so the soil quality will stay higher for longer. So that's actually a good thing. If you're going to do it for biofuel production, pyrolysis is probably the better way to go, because the lignin makes the conversion of cellulose into sugars, et cetera, and subsequent fermentation more difficult. So probably better to do that kind of biomass through pyrolysis if it turns out that it does cause lignification. So the objectives of this part are, we already looked at this, is the first two objectives we look at above. So just look at growth enhancement, quality, and then determine the effects specifically on densification capacity. I just got AgriWorld here. It's one of the industrial partners that we'll work with that's working on one of our newer biostimulants. So the methods, a set of biostimulants evaluated for ability to enhance crop yields. We apply the material as foliar spray. Generally at the mid-vegetative stage, we include a set of that represent the foremost Canadian field crops. So we have corn, wheat, and canola. We have a biomass crop, switchgrass, and we also have a horticultural crop, tomato. So the data were collected on biomass yield. This is, if you're talking about the switchgrass, for instance, it's all of the yield. If you're talking about the other ones, it's the yield minus the food material. So it's the crop residues. Biomass samples have been sent to UBC for determination of compressibility, and they are very kindly working away on this. And I'll show you the first little bit of data we have in a minute. So the results, in general, what we find with these kinds of things, these biostimulants, is say many of them help plants deal with stress. So we often see yield increases, but it's not completely consistent because this interacts with the environment. If there's more stress, there's more effect. And if there's very little stress, there might be no effect. So it varies. And but because the concentrations required are low, it's inexpensive. So this still works for producers. Yeah, so I say often clear effects when there's at least some stress present. And I've just got here, by way of an example, these are Arabidopsis plants. These are not crop plants. These are lab beasties. But this is no sodium chloride, no salt stress. And these ones all the rest of them from here over have 150 millimolar salt stress. And you can see here, if you just look at the 0 to the this is the salt stress with no signal compounds added. And you can see it, the salt stress level, 150 millimolar, has reduced the plant to about 1/10 the size of the zero salt control. If we look at the addition of those lipocyto-oligosaccharides, the LCOs, we see restoration pretty much of the plant size. And if we look here, Thurston 17, this is when we isolated the Bacillus thuringiensis strain that produces this here at the McDonald campus, and we isolated the compound that it produces, which is Thurston 17. It's a small peptide, and it again works at very low concentration. In fact, vanished in low concentrations, all the way down to 10 to the minus 11th molar. So I've actually taken to calling these things hormones of the holobiont because they're communicating, and that's all they're doing is communicating between the microbes and the associated plants. So this is some results from some of the experiments. So this is corn yield, and this is actually grain yield. And we can see here that this is the control. And what we've done here, we've got, we're fiddling here a bit, but so we get higher concentration and a lower concentration of the biostimulant, and it was applied sort of mid-vegetative. This will be the 6-leaf stage in corn. And here we applied it about a week later. So it had two or three more leaves, depending on the weather, by the time you get to here. And what you see here in terms of yield, it's nice increases, so that's good. But bear in mind, this is a single site year, so this one looks good. So if we look at biomass, in fact, even at the best concentrations, no increase. Wheat, so wheat, we're not seeing much on yield with the best concentrations, and we're not seeing on timings, and we're not seeing much on crop residue biomass either. For canola, however, at the later application, and in either concentration, we're seeing some nice increases in yield, and we're also seeing some increases in overall biomass production, so crop residue production. So it's again, each of these is single year, so we need enough data to get a sense of what it'll be like, what it's likely to be across a range of field conditions. Switchgrass, we have increases that range from relatively modest up to a full ½ ton per hectare. Biomass crops, it's one of the interesting things about biomass crops. There's extra considerations here. They would probably be grown on more marginal lands to avoid competition with food crops, and particularly the way things are going with food prices right now. Crops grown on marginal lands are more stressed more often because these soils have various limitations. And enough soil carbon sequestration and improved crop stress, some of these soils could move out of the marginal category, the ones that are least marginal. So a tomato application of in this case, a flavonoid-based biostimulant, increased fruit size, fruit number, fruit weight, but no increasing crop residue biomass. Again, this is this particular site. Okay, this is the last actual slide here. This is biomass quality effects. So we're looking at all the crop material for switchgrass, just the residues for the others, but these have been sent to UBC. Method's been tested and it's shown that it works. Recently received the first bit of data back from an experiment with them, and it doesn't seem to be much in that particular experiment. The maximum difference between the control and any treatment is just 3.5%. So Dr. Sokensender's group is going to present the rest of this, and there we go. The next bit's components 2 and 3. All right, I think we're waiting for. Okay, we're waiting to the end for questions, right? So here we go. Yes. I'm out of here, and I'm going to stop sharing. Okay, back to you.
Thank you, Doc. Okay, the next one is Hamid, who's going to quickly provide some slide on component number 2. Hamid, over to you.
Okay, thank you. Yeah, so we have done some testing on the samples we received from Dr. Smith research group. The type of experiments, measurements we did was mostly the fundamental properties of the biomass, moisture content, calorific value, the way that material has been received, how we can grind them, grindability and compressibility. So we received 7 samples: corn CXC, soybean CXC, cucumber, summer squash, eggplant, and tomato. What we did was that we ground these samples using a knife mill, a 4mm screen size, and we measured the moisture content, grinding property, size distribution, and heating value. The main difference, we observed here in calorific value was that the summer squash had significantly lower calorific value than others, but corn CXC and soybean CXC had a calorific value larger than 18 megajoule per kilogram dry basis. But the moisture content of all of them were again in the in the range of 9 to 10%. Next slide, please. During grinding, what we did was that we measured the amperage of the grinder and converted to the amount of energy that was consumed during grinding. It's a very interesting test to correlate the mechanical property of the fiber properties to the grinding measuring energy consumption. So what we also did was that we tested wood chip as a baseline to compare all of the results with the wood chip, as a baseline biomass. The observation was that corn CXC had significantly larger grinding energy consumption compared to all other biomass, but tomato was kind of in the range of wood chip. But all other tested biomass were less than half of the energy, grinding energy for wood chip. After grinding, we analyzed the size distribution. We measured the size distribution and used the standard of ASAE S319 to convert the raw data into 3 size categories of D16, D50, and D84. They are cumulative. They have cumulative concept. For example, D16 is the particle size that 16% of the bulk of biomass is less than that size, or D50 is the particle size that half of the bulk of biomass is smaller than that size. So these 3 are reported in the standard ASAE, and we calculated these 3 parameters. So for example, we see that the corn CXC, the range of particle size is larger than summer squash because it has larger D16, D50, and D84. So then in the next round, we are going to, for each of these species, we are going to test different treatments and compare, to see the influence of the various treatments on the size distribution and particle size of the material during grinding. So next slide, Mahmoud. The next test, which is the main test that we need to do, is the compressibility of the material. We plan to make multiple single pellets, 6 millimeter diameter and larger than 10 millimeter in length pellets using our hydraulic press at UBC. What we need to do is that we make at least 10 pellets from each sample at different treatment levels and compare the durability and density of these pellets as quality indices to correlate the influence of these treatments to the pellet quality. So this was a very, very short work that we have done at UBC today on this component. I will pass it to Mohammed. I know we are over time a little bit. I know that he has some interesting slides to show.
Yeah, thank you, Hamid, and thanks everyone for attending this session. My name is Mohammed. I'm a PhD student at Biomass and Bioenergy Research Group, and the focus of my work is on component 2 of activity 13. So we're working with our industrial partner, Bar Ag company, which is located, as you can see on the map, at Olds, Alberta, which is a city between Calgary and Edmonton. And they're one of Canada's leading exporter of animal feed, and they're able to provide any grade of hay and forage to the market. And the overall objective of my project is to reduce energy consumption of Bar Ag drying operation, which is used to reduce the moisture content of different animal feeds such as Timothy hay, alfalfa hay, mixed hay, and also corn silage, and grains such as oats, barley, and wheat, in order to meet the regional and international quality standards. So as you can see in this slide, it's a Google Map view of their operations. And they have a large drying operation on their site. Feed and grain drying is very energy intensive operation, and based on their reports, it contributes to 30% of their total export costs. And in terms of numbers, they're spending around 20 to 25K on their gas bills in a monthly basis. So at the moment, they're using natural gas as a fuel source with this rotary drum dryer that they're using. And with the introduction of federal carbon tax since 2019, the cost of drying keeps increasing, and it's very critical for their farm business to reduce the fuel consumption and also reduce the carbon footprint of their operation. Next slide. We are in touch with their team on a weekly, bi-weekly basis. We have meetings, and what we found out about their challenges with their drying operations. So we sat and designed a two-step drying system, which can be seen in this slide for their drying operation in order to save energy and also minimize fire risks and safety issues in the unit. So we developed a process flow sheet outlining the proposed physical systems. First step would be recovering wet silage from the silage peat. And after that, feed the silage into a pre-dryer to dry the wet silage from an initial of 70% moisture content to an intermediate moisture content of around 40%. And also fractionate pre-dried silage to small and large particles. So we can feed the large particles to the main high temperature dryer to dry the biomass to around 10% and feed a blend of small particles and large particles to the cooler directly to reduce the product's room temperature and to even out moisture content of the material. And finally, convey the dried and cooled silage to the compactor bale maker. So the approach that we considered in designing this system was to increase evaporative capacity of the rotary dryer by adding this preheater, which would decrease the drying temperature at least by 100 degrees Celsius, and also recirculating the waste heat from the high temperature exhaust back to the pre-dryer. Next slide, please, Mahmoud. In order to have a better understanding of the entire system, a mathematical model of this design was developed to represent the unit operations outlined in previous slide. So we are using this model to integrate the proposed and designed pre-drying system with fractionation operations with the existing silage peat and also dryer and cooler that they have on site. So we calculated a detailed energy and mass balance based on optimal airflow, silage flow, operating temperatures, and a degree of recycling of exhausted air from the main dryer system in order to be able to specify the optimal dimensions, capacities, and energy conserving features such as I mentioned, recycling waste heat to minimize energy input. We run the model for three cases as can be seen. I color-coded them in this slide. And among those scenarios, the model showed us the base case scenario would be the case when we recirculate the waste heat from the main dryer, and in that case, we can use it in the pre-dryer unit, and we're able to increase energy efficiency of the entire unit up to 28%. And the development of this model in our group's view can fulfill an urgent need in rotary drum drying research, not only as energy saving feature, but also to minimize fire risks in such dryers. Next slide, please. To validate the mathematical model that we developed, we're using a few data available at the site, as well as experimental data that we are conducting experiments at our labs, and also from previous research works that my colleagues have been done. And to validate the model, a lab scale dryer was fabricated and drying experiments were performed. So we're investigating experimentally the drying temperature, drying rates of fractionated wet silage, which was sent by Bar Ag to our lab here in UBC. And also we measured like material properties such as particle size distributions, densities at every stage of the drying. So at this stage, we're examining how our model predictions for the moisture content of the material, air temperature, air relative humidity is matched to the experimental observations. Here, as you can see, I did a screening on the as received materials, corn silage materials, and we found out like we have around 63% fraction of larger size materials around above 4 millimeter, and mid-sized materials are around 27%. And small size materials are around 11% of the whole sample. And when we do pre-drying from 70% to around 40%, that's our like desirable moisture content in order to insert the material directly to the main dryer itself. So it's an ongoing project, and lots of lab tests as well as simulation is going to be conducted to finally come up with an optimal design of the system. And I'll hand it over to Mahmoud to talk about success factors and future works of this activity. Thank you very much.
Thank you, Mohammed. Thanks. So as I mentioned, activity 13 had 3 components, and the last one is on demonstration of a mobile ag pellet unit. So Hamid actually mentioned that a couple of times, that we purchased a mobile containerized unit, as you see that actually on the right-hand side, and it has all of the elements to pre-process and also produce ag pellet from from agriculture biomass. So in order to demonstrate this unit, we have been working with a farm business in Didsbury, Alberta, like Westway Farms Ltd operation. And they have about 7,500 acres of grain, and they have been actually looking for a market to produce ag pellet and then use it for different applications. So we sent, the progress we have had so far is that we received this equipment from Sweden in 2021, and as Hamid mentioned, that we certified that with CSA inspection. We also did some initial testing at UBC to make sure the equipment is fine. And in February 2022, we shipped it from UBC lab to Didsbury in Alberta. So right now, actually, the equipment, as you see, that is located, it is sitting in a container. And that's the purpose, because we want to, again, show that this is a mobile unit, so we can move it around to pelletize agriculture biomass in different farms. So right now, as I mentioned, it's located here. The farmer actually has made a good progress. And they also have certified unit at their farm. They have to do that. They have completed the electricity connection. And at the moment, the next step is just start operating the unit and produce ag pellets. So that's going to be the progress by end of March 2023, which is actually the end of the Biomass Canada cluster cycle 1. So that we will provide more details on this demonstration project, hopefully in the next webinar. That's basically the progress for component 3. In terms of the relevance, again, we are trying to generate data and also analyze these data to help farmers to make better decisions. I guess that's the main purpose of activity 12 and also 13. And as, for example, Mohammed showed the different data on size distribution and also in terms of the moisture content, the more information we have from the farm data, that's going to help us to develop models and also verify those models. And then we can actually make these models available to farmers to use it and make better decisions. And the focus again on advanced drying system. As Mohammed mentioned that, again, drying, as you know, is a very energy intensive operation. The carbon pricing is actually impacting farmers. Even they are using natural gas. I mean, many people say that natural gas is not really impacted that much by carbon pricing, but actually the farmers, because they're using a lot of energy to dry their feed and also for biomass, they already told us that they are actually paying almost 30% more by using natural gas because of the carbon pricing. So that's actually the purpose to develop this advanced drying system to improve the efficiency and reduce the energy consumption. And of course, we talk about that a lot. You know, one of the lessons we learned from demonstration project, like purchasing equipment from outside of Canada, bringing it to Canada, certified, sending to a farm. Actually, we learned that that's not an easy process, even for such a small scale mobile unit. And we hope that that's going to be a lesson learned, and that we are hoping we actually publish a document on the lesson learned from purchasing equipment and then install it at the farm. So that's going to be, we realize that there is a lot of complexity associated with that, because it looks like an easy process, but it's not really that much easy process. Success factor, we are trying to identify a peak processing pass phase for farmers that they are using, again, a lot of energy. For now, we are focusing on drying, but as we mentioned, that grinding is also energy intensive process and to deal with the moisture content. So that's at the end of this project, the purpose is to identify that pathway for farmers so they can reduce their energy consumption and also produce less greenhouse gas emission. And design a new dehydration system. I guess that's I mentioned before. So that's going to be another success factor for activity 13. And the work we plan to finish by March 31st, 2023. I guess I mentioned most of that. It's again, we are trying to develop a model to simulate the whole process from harvesting the biomass to producing a product that you can either export to international market, even use it for domestic market. I think data is very important. As you know that without having access to the good quality data, doesn't matter how advanced is your model. So we are spending a lot of time with the farmers to even develop a terminology for data. Sometimes when we talk about the data, that's farmers have a different definition of that data. So we are making sure that we actually develop the same language for collecting the data. So that's going to be the focus for the next couple of months. Carbon intensity, because we talk about energy consumption, we talk about carbon pricing. So estimating the carbon intensity of that biomass processing operation is very critical, again, to show that we are actually reducing the greenhouse gas emission. And I mentioned that before that we are working with the farmers in Beachbury, Alberta. The company name is Four Peak or Winter Green, and we already installed the equipment, but the purpose is to operate the unit and produce actually tonnage of ag pellets. And that's going to help actually Fahima to do more advanced storage and handling testing. So that's going to be one of our deliverables by end of March 2023. I guess with that, we are done with the presentation. I guess we have time for 5 minutes if there is any question from the audience, even comments. So if you have any question, comments on the presentation, we would be happy to hear that. Other than, if not, then I guess we can wrap up the session. I don't see any question. That was a lot of, I'm sure that lots of information, lots of progress on activity 12 and 13. You have the emails. We are going to post a slide on the website. So if you have any follow-up question, comments, or any potential collaboration with both Dr. Smith's research group or BBRG, we would be happy to hear you. So thanks again for attending, and thanks to all of the presenters for staying with us for almost 1.5 hours. And hopefully we can see you next week, which is going to be the update on 2 other activities at Biomass Canada lesson. Okay, thank you and have a good day.
Thank you, Mahmoud.
Thank you.
Thanks, everyone.
Thanks,
Thank you,
everyone.
everybody.